So the interesting thing to me about the nonlinear systems of differential equations is that you're often going to have more than one equilibrium, which is certainly a change, right? Because up until now, every time we've done this, linear system of differential equation stuff, our equilibria has been the 0.00, and that's just kind of it. But now we're going to see a change. So let's look at this example. And I guess I'll try to use his notation, even though it's more of a pain to write out. It's fine. So let's say we have these two differential equations. dx1 dt is 3x1 minus x1 squared minus x2, and dx2 dt is equal to x1 minus x2. Definitely, this is a non-linear system of differential equations. And typically, what we do with this nonlinear system of differential equations, well, we're still going to find the equilibrium the same way we always would, by setting each equation equal to 0 and solving. In class, he's been calling this first equation f1 of x1 comma x2, and the second equation f2 of x1 comma x2. You'll see other people maybe call them f and g instead of f1 and f2, but either way, fine. So we're going to solve. So to find equilibria, we're going to set and solve both of them equal to 0 simultaneously. I should point out, when you set just one equation equal to 0, you're finding a null cline. When you set both equations equal to 0, you're finding an equilibrium, which is where different null clines cross. So if you think back to the examples we've seen before, that have been linear, and we graph the two null clines, and they cross at the origin, that's not a coincidence. Null clines of different types will always cross at equilibria, which is kind of neat. Now, which is all we've seen so far. It's, when we start talking about these non-linear ones, you're going to start seeing null clines crossing themselves because you have like two different null clines, but we're not quite there yet. So just get a lot of stuff. So we're going to set each of these equal to 0. So 3x1 minus x1 squared minus x2 equal to 0, and x1 minus x2 equal to 0. And it's usually a good idea to kind of deal with the easier one first. Now, you might notice neither of these are actually going to give me a value right off the bat. Sometimes they will. Sometimes you get like x1 equal to 5. I'm going to look at this one, which looks easier, and say, oh, well, if that has to be 0, then x1 has to equal x2. So every equilibrium is going to be an ordered pair like 1, 1, 2, 2, 3, 3, 4, something like that. Not all of those, because we also have to satisfy this equation, but we know that they have to meet that criteria. So then we're going to plug this in here. And I'm going to say, okay, I've got 3x1 minus x1 squared minus x1 equal to 0. I'm subbing in x1 for x2. And then I'm going to get, let's see, 3 minus 1. So I'm going to have, that's going to be 2x1 minus x1 squared equal to 0. Factor out an x1, left with a 2 minus x1. So then we're going to get x1 equal to 0 or x1 equal to 2. Which is then going to mean that our equilibria are going to be, well, if x1 is 0, then x2 has to be 0 because x1 has to equal x2. So one of them is going to be the point 0, 0. We're going to get that from when x1 equals 0. Or we're going to get when x1 equals 2, x2 also has to be 2. And we're going to get the equilibria 2, 2. So these are our two equilibria for this nonlinear system of differential equations. And we can check, right? If you plug in 0, 0, well, clearly 0, 0 is easy as 0. If you plug in 0 here, for both of them, they're going to be 0. Plug in 0, 0 here, it's going to be 0. Plugging in 2, 2 has a little more work. Let's check. 2 minus 2, that's 0. Plugging in 2 for x1 and 2 for x2, I get 6 minus 4 minus 2. Oh yeah, that's also 0. So both of these points are equilibrium. They make both differential equations equal to 0 at the same time. In class, he did a good explanation of talking about like what essentially how we're going to take this nonlinear system and linearize it, and then talk about epsilon 1, epsilon 2. It's kind of a lot, right? Like it feels, I definitely was like, oh, I've never really, actually I was watching, I was like, never heard anyone like explain it so clearly. Like this is really good. Like he's doing, I've never gotten such a nice kind of picture of what's actually happening here before. But to be perfectly honest, even though it's good to have all that background, the mechanics of doing this is very straightforward. The mechanics are going to be, we're going to find the Jacobian matrix, and then we're going to determine the stability based on the usual kind of way we determine stability, which is looking at the eigenvalues. So it's the same kind of process, just there's an extra little step of finding this Jacobian matrix. And again, I want to remind you that Jacobian matrix is essentially acting like the coefficients of the linearization, but it's also acting like the coefficients of your differential equation. So let's find the Jacobian, and then I'll say a little bit more. So the Jacobian here, and this is where I really find his notation kind of hard to write. I'm going to try it anyway. So the Jacobian is the first function f1's derivative with respect to x1. And then the first function's f1 derivative with respect to x2. See how that's kind of just terrible. And then the next one is f2's derivative with respect to x1. And then f2's derivative with respect to x2. The way I typically remember it is each row has a different function. Each column, you're taking a derivative with respect to a different variable. So the first row, it's all the function f1. The second row, it's all the function f2. The first column, you're differentiating with respect to the first variable x1. The second column, you're differentiating with respect to the variable x2. I often, when I'm writing this, do this. I'm like, okay, this row is f1. This row is f2. This column is x1. This column is x2. It just helps me remember what's going on. So then we're going to find the partials. So the derivative of f1 with respect to x1 is going to be 3 minus 2x1. And the derivative of f1 with respect to x2 is going to be negative 1. The derivative of f2 with respect to x1 is going to be 1. The derivative of f2 with respect to x2 is going to be negative 1. Unlike previously, well, I should, no, that's not even. Okay, so now we're going to look at this Jacobian at the two different equilibria. So first, we're going to look at the Jacobian evaluated at 0, 0 is real not exciting, but fine. So looking at J of 0, 0, we're going to get that it's equal to, I'm just plugging in 0 for x1 and 0 for x2. So we get 3, negative 1, 1, negative 1. Now, before we analyze this, let's just say a little about what we're saying here, really. What we're really doing is we're saying, okay, near the point 0, 0, so around 0, 0, our system, which is not particularly nice, our system, dx1 dt equal to 3x1 minus x1 squared minus x2, and dx2 dt equal to x1 minus x2. Near this point, our system acts like a system that's linear with these coefficients, meaning it's acting like dx1 dt equal to 3x1 minus x2 and dx2 dt equals x1 minus x2. Sorry, we can't see that. That's what we're saying, is that near this point 0, 0, our system acts like this system of differential equations. And for this system, we know how to analyze the stability of our equilibrium 0, 0. There's probably like 3 different ways we can do it. Let's see what we get if we look. I really like looking at the determinant and trace. I'm hopeful it's going to work out here. I don't actually know. So let's look at the determinant. The determinant of this matrix is going to be, let's see, negative 3 minus negative 1. And we're done. Because if the determinant's negative, what do we know? Oh, go, yeah. So I took, so really, oh, let me actually make sure. Yeah, that's right. So what I'm really actually doing, there's two ways you can do it. What I personally was doing is I was looking at the matrix and I was just saying, oh, I'm getting, my matrix, which is 3, -1, 1, -1 times x1, x2 equals dx1 dt, dx2 dt. That's what I was doing. But you could have also literally taken, no, it doesn't really work that way. You really kind of have to do it that way. I thought there was another way I could do it. There isn't really. So yeah. We'll do it again for the other one, just to kind of contrast. So I was going to ask you all a question. Having found the determinant, I haven't even found the trace yet, but having found the determinant and gotten this particular value, what do we know is happening around this equilibrium? It's not imaginary. Well, so it, how do I know? It would be imaginary. So we would have imaginary if the trace squared -4 times the determinant was negative. So if you remember that kind of the two-dimensional graph with the parabola where we talked about where the different solutions were, and if your determinant was negative, you were on the bottom where everything was a saddle. So if your determinant's negative, saddle automatically. We know it's a saddle. Another way you could think, I could have said something better maybe. Another way you could have easily, semi-easily gotten there is remember that the determinant is equal to the product of the eigenvalues. So if the product of the eigenvalues is negative, they have to have been opposite signs. So we have one positive, one negative, which means we definitely have a saddle. So the system is acting like a saddle near the origin. Let's look at the other equilibrium. Then if we'll do cool stuff. Sorry, let me get ready for doing neat things. Oh, let's come back over here. I don't know why you do that sometimes. I want you over here for now. Okay, cool. So we're also going to look at the other one. So we're going to look at the Jacobian evaluated at the other equilibrium, J of 2, 2. And so I'm just taking my Jacobian and plugging in 2 for x1 and 2 for x2. Obviously, there's nowhere to plug in 2 for x2. But so we're going to get 3 minus 4, so -1, -1, -1, -1. And then what I would say about this is, just like I said over here, what we can observe is near the point 2, 2, our system is acting like the system where these are our coefficients of our differential equation. So dx1 dt would equal -x1 minus x2, and dx2 dt would equal x1 minus x2. The parts I've written in red here are totally unnecessary, right? Like I've never even, honestly, no one's ever said it like this in my experience before, but it just seemed like a way of understanding, oh, we're really just saying this nonlinear system is acting like this linear system right here. It's very, very, very much like in 17a, when we talked about linearizations, and you talked about how if you take a line and you draw the tangent line near the point of tangency, they act the same. That's all we're saying here, just in kind of a bigger setting. We can also analyze what's happening here. So let's see, let's look at the determinant. So the determinant of J of 2, 2 is going to be -1 times -1 minus -1 times 1, which is going to be 1 plus 1, which is 2. Okay, so the determinant's positive. That really means kind of anything except being a saddle can happen. And then let's look at our trace. So our trace is -1 plus -1, which is -2. So at this point, I don't know. Do I do? I don't know. Do I not know? So it would be hard for me at this point to determine what's going on, right? Because I know the determinant is the product of my eigenvalues, and I know that the trace is the sum of my eigenvalues. So I have two numbers that multiply to positive. So they're either both positive or both negative. Oh no, we do know, right? Yeah. See, this still I kind of like this method most of the time. So they're multiplying to a positive, they're adding up to a negative, so they both have to be negative, right? If they add to a negative, so if they add to a negative, one could be negative and one could be positive, right? Because it could be more negative. But if they're multiplying to a positive, the only way to add up to a negative is for them both to be negative. So they both have to be the same sign. So both are negative. So we have a stable node or a sink. But I feel like I feel like I might have led you astray here a little bit. So let me be a little more careful with my work, because I feel like I've lied to you. So let's go actually find our eigenvalues for real. So if we do it the trace determinant way, it's going to be the trace, which is -2, plus or minus the square root of the trace squared minus 4 times the determinant all over 2. Yeah, I totally lied to you. Sorry. -2 plus or minus the square root of 4 minus 8 is -4. So I don't actually have a stable node. We have a stable spiral because our eigenvalues are -2 plus or minus 2i over 2, or -1 plus or minus I. So it is possible to have imaginary eigenvalues that definitely add up to a negative and multiply to a positive. So I guess we should take the lesson of being careful when checking our work, right? We can't just, I guess I should say, if you determine it's positive, you really do kind of have to check and see what's going on. I want it to be like, no, you don't have to, but you totally do. So we have a stable spiral. Cool. And so now what I want you to see, I think it's neat, and not just neat, I think it's worthwhile. So if we actually plot this system in a phase plane plotter, oops, oh my gosh, go away. What are you doing? Sorry. So let's see, our system was, we had 3 times x1, and we use x for x1. So 3 times x minus x squared minus y. And the next, whoops, that's a minus, not an underscore, please. And then the next one's going to be x minus y. All right, let's hope this looks as good as I think it's going to look. So look, check this out. Oh yeah, it's cool. It's super cool. So over here at 2, 2, look, it's a spiral near 2, 2. So if you're close enough to this equilibrium, you have a stable spiral. But if you move too far away from it, other things happen. So at 0, 0, 0, 0, oh yeah, 0, 0, we said we had a saddle. And it's definitely looking saddly. So kind of neat, right? Like we actually have the things that we're saying happening near particular equilibria happening near them. Now, I should clarify, right? This system only acts like a saddle if you're quote unquote close enough to the origin. How close? I couldn't say. Similarly, the system only acts like a stable spiral close enough to the point 2, 2. And again, I couldn't say exactly how close, but you can certainly look at these graphs and kind of see, it looks like this line is kind of a dividing line. If I'm over here on this side of this line, I'm spiraling in, and if I'm over here, oh, I'm moving away. So there's some sort of dividing curve or line right here. It looks like it's like whatever that is right there. It's probably some sort of eigenline, although certainly definitely more challenging to find in this situation because we don't have a normal kind of matrix. So it's kind of cool. I like this. Pretty neat. Let's do, should we do one more example? Yeah, let's do one more. Yeah, it's good to practice this stuff. And then we will do, yeah, then we'll do that. Let's see, we want to do that one, we want to do that one. Sure, we'll do this one. So, finding the equilibria, or sorry, yeah, no, the equilibria can be a little bit harder with these nonlinear differential equations. So here's another example. Let's say we have dx1 dt equal to, I'm gonna make it challenging. 10x1 minus x1 squared minus 2x1 x2. I'm gonna call that f1. And then f2 is gonna be dx2 dt. Yeah, sorry, thank you. Good call. Yes, definitely. Thanks. Good call. F2 is going to be 10x2 minus 2x1 x2 minus x2 squared. And we're going to set each of these equal to 0. So we're going to find the equilibria and classify. And we probably do some graphing as well. I'm also going to point out just ahead of time, this one's going to end up having 4 different points of equilibria. So this looks a little complicated. Let's work with both of these equations. So if I set this first one equal to 0, there's something I can do that's going to make it a lot easier. I'm going to factor as much as I can. And I can see that each one of these terms has an x1 I can factor out. So then I'm left with 10 minus x1 minus 2x2. Similarly, I have 10x2 minus 2x1 x2 minus x2 squared equal to 0. I can factor out an x2. Something I've noticed over the years that's probably worthwhile to mention is if you look at these two equations and you see that they're symmetric, meaning if you took all the x1s and x2s and interchanged them here, and you got this equation here, that would be what I mean by symmetric. And if you see something like that, what usually ends up happening is all of your solutions come in pairs, meaning if 0, 3 were to be a solution, then 3, 0 would also have to be a solution because you're able to interchange x and y and get the other one having the same type sort of deal. So that's something to kind of look out for. If you see, because it's not an uncommon thing that you would see some symmetry like this. So if you notice this, you'd be like, oh, if 4, 7 is a solution, I'm also probably going to get 7, 4 as a solution. We'll see what we mean in just a second. So I want both of these to be 0 at the same time. What's one for sure, definite, easy answer? Like x1 could be, and x2 could be. Right. So that's often, it's not always a solution, but it's often a solution. So x1 could be 0 and x2 could be 0. But, so that's one possibility. 0, 0. Let's put them over here. But I could also have x1 being 0 and this other thing being 0. 10 minus 2x1 minus x2 equal to 0. Right? I just need both of these to be 0 at the same time. So if x1 is 0, well, that one's done. That left equation is going to be 0. And instead of saying x2 is going to be 0, we're going to make that one 0. But then if x1 is 0, I can simplify this. So then this is going to become, so if x1 equals 0, I'm going to get 10 minus x2 equal to 0. So I'm going to get x2 equal to 10. So x1 can be 0 and x2 can be 10. That's also an equilibrium. And in a similar way, here comes the symmetry. If x2 is 0, x1 could be 10. So I could also have this. So then if I have this one and this one, oh, well, if x2 is equal to 0, I'm going to get 10 minus x1 equal to 0. And I'm going to get x1 equal to 10. So it's another equilibrium. And then the last one, which is kind of the hardest. So basically, there's two ways this equation can be 0, and there's two ways this equation can be 0. And I need to find all possible combinations. So both of these can be 0, or this one and this one can be 0, or this one and this one can be 0, or this one and this one can both be 0. So essentially, I'm going to use both of these equations and solve for one and plug it into the other one. So I'm going to have 10 minus x1 minus 2x2 equal to 0. I'm going to add x1 to both sides. So 10 minus 2x2 equals x1. And then I'm going to plug that into the other equation, 10 minus 2x1 minus x2 equal to 0. So I'm going to take that and drop it in right there. So then I have 10 minus 2 times 10 minus 2x2 minus x2 equal to 0. So simplifying, I've got 10 minus 20 plus 4x2 minus x2 equal to 0. So I'm going to have 3x2 minus 10 equal to 0. So x2 is equal to positive 10 thirds. And if I plug that back in to find x1, x1 is going to be 10 minus 2 times 10 thirds. That's going to equal 30 thirds minus 20 thirds, which is 10 thirds. Sorry, yeah. Sorry, I know 30 thirds, not 30th, apologies. Minus 20 thirds is 10 thirds. So I get the point, 10 thirds, 10 thirds. And these are our 4 equilibria. Before we analyze them, I want to also graph the null lines because I want you to see a thing. And normally I would graph the XY coordinate system using just regular black. But since those are some of my null lines, I actually don't want to use it. So let's see. So let's graph the null lines. You can hear our equations. We have dx1 dt, and I'm going to write it factored this time. x1 times 10 minus x1 minus 2x2. So my null lines for this one are either going to be x1 equal to 0 and 10 minus x1 minus 2x2 equal to 0. And to make it easier to graph, I'm going to think about, actually, we could totally graph this. This is going to be a line. You could solve for x2, right, to make it like a y equals something. But this line isn't too bad to graph. You can graph this line by noting that the x1 intercept is going to be positive 10, because if you set x2 equal to 0, you get x1 equal to 10. And the x2 intercept is going to be positive 5. Because if you set x1 equal to 0, you're going to get 5. So x1 equal to 0 is my y-axis. I know, so it's always weird when you're going from x1 and x2 to x1. So, right, we're thinking of x1 as x, we're thinking of x2 as y. So if x1 equals 0, I'm saying x equals 0, which is like my y-axis. So here's my null line, and I'm just going to go ahead and draw the other one in red because I know what's going to happen. So here are 2 of my null lines. Here's x1 equal to 0, and in the other equation, which I haven't done yet, here's x2 equal to 0. And then I'm also going to get for this null line, this equation here, which has, again, an x-intercept of 10, a y-intercept of 5. So it looks like this. And then the other equation, which was dx2 dt, equal to x2 times 10 minus x2 minus 2x1. This one has null lines that are x2 equal to 0, or y equal to 0, which is the x-axis, and 10 minus x2 minus 2x1 equal to 0, which is your line with an x2 intercept of 10 and x1 intercept of 5. So I'm just getting that point and that point. So here's what I really, really, really wanted you to see. The points where different types of nullines cross is where you get equilibria. So in red is my X2 nullline. This is an X2 nullline. And in black are my X1 nullines. And where they cross each other, which is here, 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 and here, those are our 5 equilibria. 0, 10, 10, 0, 0, 0, and the somewhat hard to find 10 thirds, comma, 10 thirds. It's kind of neat. So if you graph the nullines and you see where one type of nullline crosses the other type of nullline, you're finding an equilibrium, which again makes complete sense because you're just saying, oh, at that point right there, both dx2 dt equals 0 and dx1 dt equals 0. So you're finding where both equations are equal to 0. Kind of nice. And we said we were going to also look at the Jacobian. So we're going to evaluate the system. We're going to try to determine what kind of equilibrium we have at each equilibrium. So let's go find our Jacobian. Good times. Yeah. Please, yes. So I want to, and this is something I want to stress heavily, and it's why it's a good idea to draw your nullines of different types in different colors. Two opposite nullline types have to cross to an equilibrium. So you're right. These two nullines do cross each other here, but they're nullines of the same type. Similarly, these two nullines cross each other here, but they're nullines of the same type, right? They're both, these black ones are both X1 nullines. These red ones are both X2 nullines. So yeah, very, very good question. And definitely we don't have equilibria at those points. Yeah, thank you for asking. So then we're going to analyze each equilibrium. So we need to find the Jacobian. So back to our equations. Let's find the partial derivative. So equilibrium. Okay. So our Jacobian is, and again, this is where I don't want to write all the whatever. I want to just say, I know I need F1 in the first row, F2 in the second row, and then I need X1 in the first column, X2 in the second column. And I probably didn't give myself enough room here. I really didn't give myself enough room. Let's make this matrix a little bit bigger. So I need the partial of F1 with respect to X1. So that's going to be 10 minus 2X1 minus 2X2. And then the partial of F1 with respect to X2 is going to be 2X1. I'm sorry, negative 2X1. The partial of F2 with respect to X1 is going to be negative 2X2. And the partial of F2 with respect to X2 is going to be 10 minus 2X1 minus 2X2. Oh, fun times. So then we're going to plug in each of our equilibria. So let's start with 0, 0. So J of 0, 0 is going to be 10, 0, 0, 10. And all of you should be able to tell me without batting an eye, what are my eigenvalues here? Right. And so what kind of stability do we have? Unstable, is it a node or a spiral? No, because spirals only come with what kind of eigenvalues? Complex, imaginary, whichever way you want to say it. Yeah. So definitely, right? This is a stable node. Sorry, unstable. Oh my gosh. You guys said unstable. I was just blowing it. All right, let's look at let's look at 0, 10. So plug in 0, 10. Let's see, I get 10 minus 0 minus 20. So I get negative 10. I get 0 still. I get negative 20. And I get 10 minus 0 minus 20. So I get negative 10. And very much the same way, we can see we also have the eigenvalues right off the bat here. The eigenvalues are negative 10 and negative 10. So this is a stable node. I should write it down there. So here, lambda. We're going to have the same thing happen at the other point, 10, 0. We plug in 10, 0, we're going to get exactly the same thing because of the symmetry here. I plug in 10, 0, I get 10 minus 20 minus 0. Oh, and not quite the exact same thing. I'm going to get a negative 20 here. I'm going to get a 0 here and a negative 10 here. So it's also a stable node for the same exact reasons as the previous one. The eigenvalues are both negative 10 and negative 10. And then finally, our last equilibria, 10 thirds, 10 thirds. So now we have to be a little extra careful plugging this in. So let's, if I plug in 10 thirds, 10 thirds, I get 10 minus 20 thirds minus 20 thirds. So that's 10 minus 40 thirds, or 30 thirds minus 40 thirds, so negative 10 thirds. And if I plug in 10 thirds, I'm going to get negative 20 thirds. If I plug in 10 thirds, I'm going to get negative 20 thirds. If I plug in 10 thirds here, if I plug in 10 thirds, 10 thirds, I'm going to get 10 minus 20 thirds minus 20 thirds is negative 10 thirds. Okay, so this one we actually have to work for, right? It's not just here are the eigenvalues right off the bat. One way you could make this easier if you really wanted to is you could factor out a 1/3. You can totally say this matrix is equal to 1/3 times negative 10, negative 20, negative 20, negative 10. Or even you could factor out a 10. It's a little, I don't know. It just makes the math a little less gross. Finding the eigenvalues of this matrix and finding the eigenvalues of this matrix are essentially the same. Or at least the same enough that you can do that. But we could do it the hard way. Let's see. So finding the eigenvalues this way, my determinant's going to be that times that, so 100/9 minus that times that, which is 400/9. So I'm going to get negative 300/9, which is negative 100/3. And then my trace is negative 10 thirds plus negative 10 thirds, which is negative 20 thirds. So then my eigenvalues are looking like, oh wait, I should stop right there. Determinant's negative. I can only ever mean one thing. Saddle. Again, I cannot stress enough because it's going to happen sometimes and I don't want you to waste your time. If the determinant's negative, you have a saddle. You can't have imaginary eigenvalues. Because if you think about it, if you're thinking about, like your quadratic equation, tau plus or minus the square root of tau squared minus 4 times delta over 2. If your determinant's negative, the stuff in here has to be positive. There's no other thing that can happen, which means your eigenvalues have to be real. And then we know that they have to be opposite signs because they multiply to a negative number. So I'm going to say it one more time, at least. If your determinant's negative, you must have a saddle. Stop. You shouldn't even find the trace like I did. Okay. Questions before we talk about something a little different. So this is what I imagine you're going to do in class today, or at least, yeah, some of the class today. You're going to talk about a non-homogeneous system of linear differential equations. Non-homogeneous linear. But we are going to talk about a linear non-homogeneous system. Meaning we're kind of back in our usual situation. where we just have nice coefficients of x and y, except you can add on a constant kind of. So here's what we mean. Here's an example. dx1 dt equals negative x plus 4, and dx2 dt equals x1 plus 2x2. Definitely linear, but not homogeneous. So what do I mean when I say not homogeneous? Well, in a linear system, what we mean by that is the origin isn't the equilibrium. If you plug in 0, 0 here for x1 and x2, you don't get both equations equal to 0. Here's what this looks like as a system of equations. As a matrix, you have dx dt equal to the matrix -1, 0, 1, 2 times x1, x2, plus this extra part over here. This is the part that's making it not homogeneous. But you have this extra non-zero vector you're kind of adding on at the end. Okay, to find the equilibrium, it's still the same sort of thing. I'm going to say each equation equal to 0. So equilibrium. Oops, that's a negative x1, sorry. Negative x1 plus 4 equals 0, so x1 equals 4. And then x1 plus 2x2 equals 0. Well, if x1 equals 4, then we have 4 plus 2x2 equal to 0. So x2 has to equal -2. So that's our equilibrium. Definitely atypical. We're not used to having an equilibrium that's not at the origin. So then how do you solve the system? It's kind of weird. Like definitely, this is a topic that I took a while to wrap my head around when I was first thinking about it. But we're going to make the substitution, which you definitely started talking about in class. You're going to let some new variable, I'm going to call it y1, equal x1 minus your equilibrium point. So let's call this equilibrium x1 hat comma x2 hat. And y2 similarly is going to be x2 minus x2 hat. So in this particular problem, y1 is going to equal x1 minus 4, and y2 is going to equal x2 plus 2, or minus 2. And then we're going to solve for x1 and x2. Sure. Do we really need to? I guess. Why not? Okay, now here's something to observe about making this substitution essentially. Both x1, so both the pair x1, x2 and y1, y2 have the same, what's the word I'm looking for? Well, actually, let's write this in. So here's what I should point out. The derivative of y1 with respect to t. Well, y1 is equal to x1 minus 4. So it's going to be the derivative with respect to t of x1 minus 4. And I'm going to ask you all a question that you can answer. What's the derivative of 4? Right. So the derivative of this is just the derivative of x1 minus 0. So dy1 dt is equal to dx1 dt. And similarly, dy2 dt is equal to dx2 dt. So essentially we have the same system of equations, but we also need the following. Sorry, brain. So dy1 dt is equal to dx1 dt. dx1 dt is equal to this. But then if we plug in what x1 is equal to, it's equal to negative y1 plus 4 plus 4. I'm really just putting, that's why we solve for x1 there. I'm subbing that in right there. And that's equal to negative y1. And in a similar fashion, dx2 dt is equal to x1 plus 2x2, we're going to sub in what x1 and x2 are. So that's going to equal y1 plus 4 plus 2 times y2 minus 2, which is going to give you a y1 plus 2y2, because the 4 and the negative 4 cancel out. So here's what we're trying to achieve with this. We're trying to take our system of non-homogeneous equations and write a related system of homogeneous equations. So now, instead of having to write this thing with this 4 here, look what we've got. We've got dy1 dt equal to negative y1, and dy2 dt equal to y1 plus 2y2, which gives us the system dy dt equal to the matrix negative 1, 0, 1, 2 times y1, y2. And this is a homogeneous linear system of equations. Which we totally know how to solve. Yeah, we can do it. Okay, let's find the solution. Now, luckily, we're in a pretty good spot here. Our eigenvalues are also easy to see. Our eigenvalues are negative 1 and positive 2. So then if I want to find my eigenvectors, I'm going to have negative 1, 0, 1, 2 times my eigenvector equal to negative 1 times my eigenvector. So let's see. The first equation doesn't help. Negative x equal to negative x doesn't tell me anything. So the second equation is going to be 1x plus 2y equals negative y. So x equals negative 3y. So my vector is going to be y equal to 1, x equal to negative 3. And then for the second one, we're going to have negative 1, 0, 1, 2 times xy equal to positive 2 times xy. And we're going to get negative x equal to 2x, which tells us that x has to be what? It's not 2. If negative x equals 2x, there's only one number. Zero. You can also add x to both sides, right? But I like being able to see that, oh, if you have something times x equal to something else times x, the only number where different multiples of it end up being the same is the number 0. So we get x equal to 0, which means y can be anything. We usually pick 1. So there are my eigenvectors. And then we can write our general solution, which is that y of t, not x of t yet, right? Because we're still dealing with y of t. Y of t is equal to c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. And then finally, you go back and you substitute in what y1 and y2 are equal to. So I promise you we're almost there. This will take just one more moment. So now we're going to sub back that y1 is equal to x1 minus 4 and y2 is equal to x2 plus 2. So y1 equal to x1 minus 4, that's equal to the top part of the solution. So it's equal to c1e to the negative t times negative 3 plus 0. And look, now we've got x1. So x1 equals negative 3 c1 e to the negative t plus 4. And similarly, y2 of t equaling x2 of t plus 2 equal to the second part of this, negative 3 c1 e to the negative t plus c2 e to the 2t. We can solve for x2 by just subtracting 2 over. So we're going to get that x2 of t equals -3c1 e to the negative t plus c2 e to the 2t minus 2. And if you really, really want to write this as a matrix, you could say, okay, my solutions are x1 of t, x2 of t equal to the following. It would be, yeah. Sorry, it's a little c1 e to the negative t times, we have a -3 here. Oh, apologies, sorry. I accidentally got a -3 right there, and I shouldn't have. Right, there was no -3 in this second part. That should be a 1. Sorry about that. Plus C2. Wow, how did, oh, I'm sorry. No, that's fine. Yeah, sorry. So I've got this part here, and then C2 times e to the 2t times 0, 1, and then finally plus 4, 2. So a little extra part there gets added on as a vector at the end. Kind of neat. It's kind of, I will say, it's kind of neat. It's also kind of a giant pain in the butt. But that's, so there's kind of this long explanation to kind of circle back around to basically the whole idea into being, you find your general solution like you normally would. In fact, yeah, I know we're out of time, like by -2 minutes. I just want to say, like, the whole idea is basically, you take the system of equations, you find the, I have to do a little work, but basically you treat this like the 4 isn't there. You do your matrix thing like you normally would. You find the eigenvalues, find the eigenvectors, you find your general solution, which would be this with those eigenvalues, eigenvectors, and then you tack on this extra piece at the end.